Hello everybody, welcome back to Eurographics 2012. Hello everybody, welcome back to Eurographics 2012. So my name is Marco Livezu from CNR Remati, and I'm going to be your session chair today. So this is the short paper track number 3, Modeling and Shapes, and we're going to have 4 beautiful papers to be presented. So before we dive into the presentations, I will just remind you that you can, for the Q&A, ask your questions either in the Discord channel or on the chat box on the YouTube page. So please write your questions in both places, and I will try to do my best to keep an eye at both sources. So the first presentation is titled First Ordered Sign Distance Fields and is authored by Robert Ban and Gabor Valazek, and Robert will be presenting.
Hello there, my name is Robert Van, and I am going to present you a first-order generalization of sign distance fields. This is a joint work with Gabor Valazek. First, I will shortly recap sign distance functions and their widely used discretizations, sign distance fields, which I will refer to as order 0 distance fields. Then I will present our contribution, an extension to distance fields that incorporates the first partial derivatives of the sign distance function in the distance field samples. The theoretical basis of our generalization is the Taylor approximation. We show that this extension improves the overall storage requirements of distance field while retaining the same accuracy. Then we present a construction algorithm to convert arbitrary representations into first-order distance fields. All we require from the source representation is that the point surface sign distance can be queried. Finally, I'm going to compare our new representation to the classical one. In the first half of the presentation, I will use 2-dimensional examples for clarity, but the main focus of the work are the 3-dimensional use cases. The sign distance function of an object is an implicit representation of the object's surface. In any point of the space, the function returns the distance from that point to the surface. This means that the zero-level set of the function is the represented surface. To differentiate between inside and outside of the object, the function inside has a negative sign. It is important to note that the sign distance functions are continuous mappings, but their derivatives have discontinuities. These are in points where there are more than one boundary points closest to them, like the center of a sphere. Objects represented with distance functions can be visualized directly by sphere tracing, but most commonly they are used as auxiliary data for collision detection or advanced light effects such as soft shadows or ambient occlusion. The distance function of a simple shape like a sphere or a box can easily be calculated, but for more complex objects it may be too expensive to compute. In practice, sign distance functions are often discretized. We refer to the result of this as sign distance fields. Traditional sign distance fields are sets of sign distance function values. We only deal with regular grids of samples, but our construction can be applied to arbitrary sample spacing. Here we have a regular grid of cells, each of which contains a sign distance value. The sample position of the cells are in their centers. If nearest neighbor sampling is used, these will be the distance values returned by the previous distance field. Each point in a rectangle returns the same sample value. Now let's take a look at a single sign distance field sample denoted by the red X on the figure. Geometrically, the stored value can be represented as an unbounding sphere centered at the sample position. This sphere touches the boundary of the shape, but none of its inner points intersect the geometry. We can plot the error heat map of a single distance value for a particular geometry, in this case the red circle, where blue means low error and yellow means large error. The interesting thing to note is that the single value is precise at its own level set. For example, note the blue circle around our geometry, where the single sample is precise for this case. Although this is an interesting property, it also shows how little local information an order 0 sample can represent. But what can we say about the theoretical approximation property of this single sample? Let's treat these as a 0-degree Taylor polynomial approximation, and we have an upper bound of its error from Taylor's approximation theorem. This holds outside of the medial axis of the geometry. It also provides a theoretical framework to study the approximation properties of sample and reconstruction-based schemes, even when the sample positions are arbitrary, but that is beyond the scope of this presentation. To test the practicality of this Taylor-based interpretation, let's apply it to signed distance fields and see if using first-degree Taylor polynomials per sample comes with the expected higher local accuracy. So instead of simply storing the distance function values, we save the best linear polynomial fit to the signed distance function at every sample point. This is the first-degree Taylor polynomial at every sample point. The first order sample is composed of the partial derivatives of the signed distance function and the constant term. So algebraically, a first order sample is a Taylor polynomial of degree 1, but geometrically is just a plane. Note that for signed distance fields, this is actually interpreted as a half space, namely it is a local approximation to the inside-outside partitioning as well. The plane represented by the first order sample is usually a tangent plane to the surface or an approximation to it. In this two-dimensional example, it is shown as the green tangent line. Remember that the sample isn't just the line, but a polynomial, so it can be evaluated at any point in space. This means that it can represent the signed distance function much more precisely near the sample point. This property can be clearly seen on the error heat map. Compared to the order 0 sample, the Taylor polynomial is precise in a much larger neighborhood around the sample. Being a linear polynomial, a single first-order sample represents a signed distance function of a plane exactly. Another interesting property of the first-order sample is that for a convex object, a sample on the outside is precise on a half line starting from the foot point going through the sample position. For a sphere, this even extends until the center. Although it is possible to analytically express the partial derivatives of the signed distance function of various representations, it is less practical for piecewise linear approximations such as triangular or quadrilateral meshes, especially because the signed distance function of the closest triangle may not represent the evolution of the signed distance function of the mesh properly in a larger neighborhood. Instead of using the analytic partial derivatives, we propose to fit a first-order polynomial to a collection of signed distance samples around the sample position. For the red first-order sample, we evaluate the signed distance function in a surrounding fine grid. Then a linear polynomial is fit on these values, which will indeed approximate the Taylor polynomial. Now that we know that the first-order distance field sample is essentially a plane, and we have seen that we can fit one to a collection of distance samples, all there is left is to pick a basis to represent this linear polynomial. We want to use the GPO hardware filtering when sampling a 3D distance field texture. We also want to use the hardware filtering to simplify computations. That requires a basis where evaluation is invariant under the barycentric combination of coefficients. Simply storing the distance values and the partial derivatives separately does not satisfy this. Evaluating such hardware-interpolated Hermite coefficients does not yield the same result as interpolation of the separately evaluated approximations. You can find some extra sites at the end of this presentation. But for now, all we need to see is that the global bases do interpolate correctly. So a first-order sample is stored as shown here, expressed by the partial derivatives and evaluations of the signed distance function f. Note that the linear coefficients are indeed the partial derivatives of the signed distance function, but the constant term is not a single expression. The greatest drawback of this is the fact that we can no longer use the constant term as a signed distance function value. We could use orthogonal basis to retain this property, but that is beyond the scope of this paper. Traditional order 0 signed distance fields are evaluated with trilinear interpolation. This can be achieved with hardware filtering or by manual interpolation. For the latter, first we have to find the cell which contains the evaluation point. Then the distance values are mixed together according to the relative positions of the evaluation point. As discussed before, the same procedure works for first-order evaluation. The difference is that instead of the distance values, we mix the coefficients of linear polynomials, and the result is also a coefficient vector. Then we must evaluate the polynomial at the evaluation point, which gives us the final distance value. For the construction of a first-order distance field, first we need a source geometry, which can be any representation where point surface sign distance computation is available. The next three parameters describe the dimensions of the constricted distance field. Then we need a fine grid around every sample, which will be used to fit the linear polynomials. The last parameter is a pre-computed matrix for the polynomial fitting. This only depends on the fine grid locations. The matrix is a least square solution to the linear equation on the right. The algorithm calculates every first-order sample independently in the following way. First, we need to compute the position of the sample. Then, we evaluate the source distance function on the fine grid around the sample. These distance values are collected into a vector. Then we solve the fitting equation by multiplying this vector with the inverse matrix. And finally, the solution has to be translated to the sample position, since the matrix is calculated for the grid centered around the origin. Note that the translation only affects the constant term. The proposed construction algorithm has several hyperparameters. The first we have studied was the resolution of the per-sample fine grid, illustrated by the gray grid points on the right. We have found that the fine grid resolution has a very mild effect on the accuracy of the resulting fit linear polynomial. As a go-to, we went with 7x7x7 fine grids. The extent of the fine grid, however, is a much more impactful parameter of the construction. Essentially, it determines the locality of the approximation. From another perspective, it can be thought of a level of detail control. Here, the green points illustrate the fine grid, and the distance field sample positions are in orange. The smaller the grid, the more local the approximation is. The optimal value is content and distance field resolution dependent. We have found that for lower resolution fields, small fine grids are preferable as they convey higher geometric detail. For the tests that follow, we have used fine grids that spend 10% towards the neighboring samples. This does come at the expense of the approximation accuracy of the samples, which can be important for trilinear filtering. For example, these images were generated using trilinear interpolation too. The smaller the fine grid, the less accurate the fit sample is farther away from its sample location. For higher resolution grids, extents above 50% up to 100% are a better go-to choice. This side-by-side comparison shows how zero and first-order sign distance fields look like when they contain the same amount of samples. Note the much higher level of detail on the first-order field on the right. Another interesting comparison is how these fields look like when we let them store the same amount of scalars. The first-order field on the right still offers higher detail. The first-order representation here uses a naive approach though. Each sample stores the coefficients of the first-order Taylor polynomial in 4 pieces of 16-bit floating point numbers. This can be improved as shown in our paper. A first-order sample only possesses 3 scalar degrees of freedom because of the gradients of the sign distance function is of unit length. By using two 10-bit octahedral coordinates to encode this unit vector and 12 bits to store the sign distance, we can compress the first-order sample to 32 bits in total, that is, a single unsigned integer. This halves the storage requirement for first-order fields. This is how the previous comparison looks like when we assume that the first-order samples are packed. Here we assume that the zero-order samples are 16-bit floats, and the 4 scalars of the first-order sample are compressed to 32-bit unsigned integers. The drawback here is that unpacking also requires manual trilinear interpolation, so this can be overly expensive. It depends on the use case. The storage improvements of the first-order field come at a computational cost. It is just another space-time trade-off. We have tested performance by direct visualization with sphere tracing. The numbers here are average render times measured over 100 frames and at a full HD resolution. We render 0 and first-order fields at the same resolution. Our tests show that the query times may increase up to 28%. Although for practical cases, namely meshes, it was more up to 19%. Then again, higher accuracy means that we can use lower resolution first-order distance fields and still have the same precision. In this particular case, we have aggregated render time results of the same accuracy 0 and first-order fields. This way, the performance impact of first-order fields is reduced to 10%. Note that all of these comparisons were done using manual trilinear interpolation. If the limited precision of GPU hardware interpolation is acceptable for your use case, then the figures are further improved. Packing, on the other hand, adds a significant increase to query times. In conclusion, we have shown a first-order generalization of signed distance fields based on Taylor's approximation theorem. It is a more efficient way to utilize the available bits of storage. It means that we are better off storing first-order samples than just increasing the number of zero-order samples. This representation increases the computational cost of distance field queries. However, it can be mitigated by using smaller resolution first-order fields of the same precision. We also shown that GPU hardware filtering can be applied to this representation if samples are stored in a polynomial global basis. Additionally, we presented a general first-order distance field construction algorithm. This can be applied to any geometric representation of the source shape. All we require is that we should be able to compute point surface signed distances. We tested this construction on triangular meshes. The algorithm also supports level of detail control with the fine-grid extent hyperparameter. It is also worth noting that this construction is not restricted to signed distance functions. Arbitrary mappings can be approximated with this approach. And the samples need not to be regularly spaced either. Thank you for your attention.
So let's see if there is any question in the channels that we have available. Okay, so we do have a question, which is the following. At evaluation, do you do any renormalization or you simply evaluate the result of trilinear interpolation of GPU?
We use the interpolated coefficient vector and we don't do any sort of renormalization, because essentially what we rely on is the fact that we can take the barycentric combination of these polynomials.
Actually, I would like to add that for the packed version, when we pack the values to a simple 32-bit integer, then we actually have to do renormalization, because the normals are actually stored as into parts, which is essentially just to so they don't have the length value, so it's we assume that they are of unit length, and then we do need the renormalization for the for getting back the original vector.
Okay, so let's see if there is any other question. Okay, no. Okay, so I do have a question. Well, actually two. So the first question that I want to ask is, what happens when you are close to the medial axis of this distance field? So since you sample the grid, and then for every single sample you compute the distance to your reference shape, when you fit your first order approximation, your first order polynomial, is this reliable nearby the medial axis?
Yes, we did some tests, especially on the circle in the plane, and we have noticed that if you are on the medial axis symmetrically, so the fine grid is somewhat symmetric around it, then the Taylor linear polynomial will collapse to a constant, and that will actually be the sign distance from the boundary. And in practice, usually the fit normals, so the normal vectors of the fit polynomials are usually very close to unit length.
Nice. Okay, so just one other curiosity that I have, because I've seen in the presentation that at some point you mentioned the fact that the stencil that you use, it's sort of okay when the size is in between 2 times 2 times 2 to 9 times 9 times 9, and you ended up using 7 by 7 by 7, which was surprising to me because I was wondering, well, if you could go with 2 by 2 by 2, so the algorithm should be faster, so why using a bigger one?
There everything is pre-calculated, so that doesn't really matter. It's in the pre-calculating step, so it doesn't matter after when we are using the data later.
Oh.
So it's only for the construction, and later it doesn't. We don't use that grid anymore. So it's just for the construction part.
Okay, I didn't get this. Okay, so let's see if we have any other question from the audience, but it seems that we don't. No, I don't see any other question. So let's thank the speakers, and we can move to the second presentation, which is titled Learning Body Shapes and Pose from Dense Correspondences. And this is a paper authored by Yuzuke Yoshiyasu and Lucas Gametz, and the presenter will be Yuzuke.
My name is Yusuke Yoshiyasu from AIST Japan. Today, I'm going to talk about our deep learning method for estimating 3D humans from a single image using dense correspondences. Nowadays, it is becoming possible to estimate not only 3D human pose, but also body shape from a single color image. Our focus in this work is to tackle the problem of learning 3D humans from 2D information without directly using 3D training data, which is in practice difficult to obtain. So the question we raise and address in this work is, can we learn 3D humans from 2D information without directly providing 3D training data? Deep learning for estimating human body shape and pose started around 2016 and becoming very popular in these 2 or 3 years. These approaches can be divided into roughly 2 groups. The first one uses 2D key points to estimate and learn 3D humans. Simplify fits a human body model to 2D key points estimated using CNNs. Human mesh recovery runs body shape and pose end to end. Recent techniques use silhouettes and part segmentations to improve estimations. However, it is still challenging to train accurate and robust model that can generalize well to unknown environments and scenes. The main challenge stems from the fact that a large 3D dataset is really difficult to obtain for 3D human estimation. For example, the common dataset for 2D pose detection contains 25K images from YouTube. There are large variations in body types and clothes. On the other hand, for 3D pose detection, as it's difficult to record mocap and multi-view video at the same time, the dataset is limited to, for example, 15 actions, 5 subjects with tight clothing, and 4 viewpoints. it is difficult to learn a robust 3D pose estimation model that generalizes well to unknown scenes and environments using only 3D dataset. In general, 3D dataset contains less variations for being used in body shape learning. Body shape can be learned from 2D annotations, which contains body shape information, but supervising with 2D key points is not enough. Silhouettes are more informative about the shape, but are in general very noisy. Considering these challenges and to answer the question, can we learn 3D humans from 2D? We propose training strategy called Deform and Learn, where we alternate deformable registration and deep learning in order to learn 3D humans from dense correspondences. To start with, we create dense correspondence dataset between body surface and image points. Dense correspondence contains rich information about 3D shape and pose and less noisy compared to silhouettes. In total, we collected more than 100K images with dense correspondence annotated. The main source of our dataset is DensePose datasets from Facebook research. In DensePose, the human body model is unwrapped into 24 parts, and the vertices in each of them is annotated with part index and UV coordinates. There are around 50K images manually annotated in this dataset. We convert DensePose dataset into dense correspondences between body surface points and image points by simple nearest point searches. Let us next explain the Deform and Learn strategy. The goal is to learn a model that can predict body parameters such as shape, pose, and camera from a single image. The straightforward approach to do this is to give 3D supervisions, but this is in practice not possible for in the wider setting, since the ground truths of 3D shape and pose are not available. Instead, we first reconstruct 3D humans by fitting a template model to dense annotations using deformable registration. This is used as supervisions for training deep neural networks. The key idea in improving accuracy is to provide the prediction results from neural network to initialize deformable registration. This will reduce the possibilities of deformable registration to be trapped into local minima. And this process is repeated several times to improve accuracy of body registration in neural network learning. We call this iterative learning strategy as Deform and Learn. To reconstruct 3D humans from dense correspondences, we designed an image surface registration technique using deep learning framework. In the forward pass, the template model is deformed by model-based approach and then projected to images by weak perspective projection. Then the dense correspondence loss is calculated by taking the difference between projected body points and dense annotations. Also, joint limit loss and key point loss are incorporated. To constrain the depths of skeleton joints, we use conditional generative adversarial network, CGANs, to learn depths from 2D key points in an supervised manner, and use them to guide surface registration. These losses are back-propagated to optimize the parameters. This is some examples of image surface registration. As we can see, the human models are well aligned to images. Next, neural network is trained using the reconstructed 3D humans. The body parameters, such as pose and shape obtained using deformable registration, is fed into deep learning as a supervision. To wrap up, we have 3 steps in our Deform and Learn strategy, including CGANs. We loop these 3 steps from CGANs, deformable registration, and then deep learning. In the next round, It started from also SIGANs, then registration, and deep learning. These processes are iterated for several times. To validate our learning framework, we made experiments with these settings. For base network, we used ResNet 50 pre-trained on ImageNet. For optimizer, Adam Optimizer is used. It took 3 to 4 days with NVIDIA GPUs. Batch size and learning rate is set as follows. And for deep learning framework, we used PyTorch. For training, we use DensePose track and Human 3.6 dataset. We compare our approach with the techniques based on full 3D supervision, semi-3D supervision, and that uses external 3D data. We tested 2 annotation types for Human 3.6 dense annotations. Our SMOSH uses dense correspondences from surface mocap markers. Our DensePose uses dense correspondences estimated by neural network. For evaluation metric, we use MPJPE, which is basically the average position errors of skeleton joints for all the testing set. To validate our training strategy, we plot the error values on testing set with respect to iterations. As this graph shows, our deform and learn is effective in improving accuracy gradually as iteration increases. We tried training the model with a single iteration with more training epochs, but the error stayed high in this case. We also tried supervising neural networks with dense correspondences directly, but this was a tricky task and we could not stably train the model. Shows an example of body shape and pose estimation results, which shows improvements after each iteration. As we can see, the pose gradually get closer to the image. This is the results of our method in the wild images. Without providing 3D training data, the shape and pose are fitted reasonably to images. This is another example. Here's a comparison with previous approaches. Our method, which does not use 3D training data, is not as good as 3D supervised approaches. However, our method outperforms semi-3D supervision approaches that relies on some 3D training data and other techniques that does not use 3D training data. It is also comparable to human mesh recovery, which have access to external 3D data during training. Our SMOSH use dense correspondences obtained from surface motion capture markers on Human 3.6. Our DensePose use dense correspondences from neural networks on Human 3.6, which is purely trained from 2D data. These results indicate that the quality of dense correspondences affect the results. Here we show aberration studies on image surface registration. Without the dense correspondence loss, the shape as well as pose are not well aligned to the image. Without SIGANs, the depth is not reliable. These results show that dense correspondences and SIGANs play important roles in our system. Finally, I would like to show some videos. In summary, we proposed a method for estimating 3D human pose and body shape from a single image. As a solution to our problem, can we learn 3D humans from 2D? We propose a training strategy called Deform and Learn, which alternates deep learning and deformable registration in order to learn 3D humans from dense correspondences annotated on 2D images. We are now using multi-view images in deformable registration, and by doing that, accuracy has been improved. In the future work, we would like to accommodate diverse body styles such as children. We would also like to incorporate temporal smoothness between frames to get smooth motions. Finally, we would like to design a self-supervised learning framework for estimating dense correspondences from images sequence, as annotating dense correspondences on images is effort-taking. Thank you very much.
For this presentation. I don't know if you heard me, maybe I was mute, so I will say it again. So unfortunately, we don't have the live presenter for this last paper, so we cannot take questions for this presentation. And we're going to move directly to the third presentation of the session, which is titled Adversarial Generation of Continuous Implicit Shape Representations. And this is a paper authored by Marian Kleinberg, Matthias Fey, and Frank Wickert. And Marian will be presenting. Just a second, because it seems the author showed up like just a second lately. Not sure whether we have it or not. Okay, so it seems we have the author ready to answer questions. So if there is any question from the audience, we can actually take some of them for the previous video. Although it seems there are no questions, but I actually do have one, which is about the live demo that was shown in the video, in which at some point I've seen that the neck was going extremely stretched. And so I was wondering whether the human prior, the 3D mesh that you're fitting, is just a mesh, or is a richer model in which you also know the underlying skeleton, where the joints are, and the degrees of freedom. Because if the answer is no, essentially the question is, would you think it would be helpful to have such a knowledge in the prior in order to better fit the poses starting from the image?
Oh, so can you hear me?
Yeah, I do.
Oh, okay. So sorry, could you speak again? Sorry, I didn't catch well.
Oh, okay. So in the final part of the presentation, there was a video with a live demo.
Yes.
There was supposedly you just moving, and then you were
yes.
Okay, so at some point I saw the neck, which was becoming like extremely elongated, which made me think that the 3D model that you fit is just a mesh. Is this the case?
3D, yes, model is the mesh, and we have scale. It's not the statistical human body model for the body shape, but we have parameters for each segment. It's scaled with the to fit the image, but it's not like constraining. It's based on like 3D prior of body shape, so it's learned from images. But yeah, actually, it doesn't really constrain it as with the 3D human shape prior. So yeah, I think there are some errors in like correspondence, data sets, and so I think it's better to combine with the image data set and also 3D prior to get more like human-like. But at the same time, I want to proceed to use like multi-view images so that we can constrain more. Relying on 3D prior, yeah, it's good, but I have some like potentiality in like using images. So yeah, to extend it to multi-view images, that's the next step to make it like more humans, and using images, we can like have more data sets. So that's the next step, I think.
Okay, thank you. So let's see if we have any other question from the audience. So none of the YouTube channel.
So
Discord. Well, okay, so no, there are no more questions. So we can now move to the third presentation, which, as I said before, is a paper entitled Adversarial Generation of Continuous Implicit Shape Representations, and Marian Kleinberg will be presenting. Marian Kleinberg will be.
Short paper titled Adversarial Generation of Continuous Implicit Shape Representations. In this paper, we tackle 3 shape synthesis with neural networks. In particular, we transfer the deep SDF network architecture into a generative adversarial network, and we propose strategies for discriminators of continuous shape representations. An important question for neural shape synthesis is, which shape representation should we use? A common representation of 3D objects is the triangle mesh. Generating them involves many discrete decisions, which are difficult for neural networks. Voxel volumes are often used to represent shapes. Techniques from image generation can be applied to them. Some approaches use point clouds, however, these are often limited to point clouds of fixed sizes. Recently, some papers used implicit representations for shapes, in particular sign distance functions. Here you can see a slice through an example shape. The distance from a query point to the shape is simply the distance to the closest surface point. The sign distance function adds a sign to it that indicates if a given point is inside or outside the shape. This is an implicit shape representation, since the shape is the zero isosurface of the sign distance function. Shapes can be represented with sign distance functions, for example by sampling the SDF on a grid, resulting in a voxel volume. This voxel volume can then be reconstructed into a triangle mesh using something like marching cubes. We can also sample the SDF at arbitrary points, resulting in a point cloud that is non-uniformly distributed. Since our work is based on the deep SDF network, I'm going to give a quick introduction of the deep SDF architecture. Instead of learning a discrete representation of a shape, such as a voxel volume or a set of points, the deep SDF network learns a continuous representation. That means it takes a point as the input, and this could be an arbitrary point, and the output is an estimate of the SDF of that very point. The deep SDF network is a multi-layer perceptron, so it doesn't contain any convolutions. To learn more than one shape, the deep SDF network receives an additional input that is the latent code Z. To learn a set of multiple shapes, the authors of the deep SDF network propose what they call the autodecoder. It works similarly to an autoencoder, however it doesn't contain an encoder. Instead it's only the deep SDF network, which is the decoder, and before training they assign a random latent code to each shape in the dataset, and then during training both the latent code and the network itself are improved using stochastic gradient descent. That means that while the latent codes for shapes are random at the beginning, during training the codes of similar shapes will move to each other, whereas the latent codes of different shapes will move away from each other. However, just like a autoencoder, this approach is limited to learning just the dataset that was supplied. And in our paper we wanted to investigate if the concept of deep SDF can be applied to a generative adversarial network. Just a quick recap of what a generative adversarial network is. It consists of two networks, one's the generator and the other one is the discriminator. And the generator receives a randomly sampled latent code and generates a fake sample from that. The discriminator receives either a real sample from the dataset or a generated fake sample, and the task of the discriminator is to tell if this was a fake or a real sample. And during training, the generator can be improved using the gradients of the discriminator, and the task for the discriminator becomes increasingly difficult during training. And if it works well, they reach an equilibrium where the discriminator can't decide if a sample is real or fake, and the generator generates realistic samples. In our case, the generator of our network is a deep SDF network. Usually, however, in GANs, the discriminator is a mirrored version of the generator. In our case, this is not possible because the output of the generator is just the SDF value for a single point. And if we show that to a generator network, it can't decide if this belongs to a realistic shape or not, because it's missing the context. So we need to find a way to provide context to the discriminator. And in our work we propose two different discriminator networks that can be used in our GAN. The first one is a voxel discriminator, and that is a 3D CNN. So in our setup, what we do is first we sample a random latent code Z, and then we take a fixed grid, a fixed voxel grid, and evaluate our generator for all the points in the voxel grid. We can then reshape the SDF values of that into a voxel volume and feed that into our voxel discriminator. The discriminator is a 3D convolutional neural network, and our dataset is a set of voxel volumes that we generated from the shapes. Here on the left you can see a latent space interpolation of shapes generated this way. During training we employ progressive growing. That means that first we start with a low voxel resolution of 8 and we progressively increase it to 64. Since the generator is a deep SDF network, we can query it at any points, so we can also generate shapes at higher resolutions than it was trained on. And we use as a loss function the Wasserstein distance with a gradient penalty, which is commonly referred to as WGAN GP. An interesting finding is that our network can generalize to higher resolutions. For this we did an experiment where we trained our network with only voxel volumes of resolution 8. On the left you can see the output of our network at this resolution of 8. If we were then going to linearly upscale this to 128, you can see in the middle that it does not look realistic. However, if we take the network that was only trained on a resolution of 8 and query it at a higher resolution, in this case 128, we can see that the network was able to generalize to higher resolutions during training, even if it has never seen any voxel volume of a higher resolution for this experiment. The second variant of our GAN uses a Pointnet as discriminator. The Pointnet is a graph neural network that classifies point clouds. Again, we start with a latent code that is sampled from the normal distribution and a uniformly sampled point cloud. We then pass each point of the point cloud through our deep SDF generator and feed the points as well as the generated SDF values into the discriminator. So the Pointnet takes as an input for each point the position and a feature vector, and in our case the feature is just the SDF. Our dataset also contains uniformly sampled point clouds with the ground truth SDF values for them. It is important that the points are sampled uniformly, as the Pointnet takes as an input the SDF as well as the points. So if we didn't use uniformly sampled points, the discriminator could just look at the structure of the point cloud instead of the generated SDFs and make its decision based on that. But we found that with this setup, the discriminator can indeed provide useful feedback in the form of gradients to the generator network, so that it can actually learn to generate realistic shapes. To address the problem of missing structure in the uniformly sampled point cloud, we propose a refinement step for this GAN approach. Again, we start with a uniformly sampled point cloud and predict the generated SDFs for that. However, then as a next step, we take the points of the point cloud and move them towards the surface. This is possible because the gradient of the sign distance function will point to the surface, and since the sign distance function is encoded as a neural network, it is very easy to differentiate it and to create the gradient. So this way we can move the points closer towards the surface using the generated sign distance field. Now the point cloud is no longer uniformly sampled, and instead it's sampled more densely near the surface. And this is useful because if we are going to reconstruct the surface of this shape later with marching cubes, only the points close to the surface or close to zero matter, because they are going to influence how the reconstructed mesh will look like. Now we use our generator network again to predict sign distance values for these updated points, and then this is fed into the Pointnet discriminator network. The discriminator can now make its decision based on the sign distance values as well as the structure of the point cloud. The position update we did earlier is differentiable because it only uses the output of the neural network. So in the backward pass of this, the gradient of this position update will be the second derivative of our generator network. So then this refined point cloud is once again fed into our Pointnet discriminator, and now the Pointnet discriminator can take the structure of the point cloud as well as the attached SDF values to make its decision. For this to work, we need to make sure that the dataset point clouds and the generated point clouds have the same statistical properties. That means the dataset can no longer be uniformly distributed points, and instead the points need to be sampled more aggressively towards the surface. If this wasn't the case, the discriminator could simply look at the structure of the point cloud, and again it would not learn anything. Here you can see some shapes generated with our Pointnet discriminator-based GAN. In the top row you can see the GAN that uses only the Pointnet as a discriminator, and in the bottom row you can see the Pointnet discriminator with the refinement step. For our project, data preparation turned out to be a non-trivial task. We worked with the ShapeNet dataset and especially the chairs and airplanes categories. The task is to determine the SDF given a mesh and a set of query points. These query points could be a voxel grid in the case of the voxel discriminator, or an arbitrary point cloud in the case of the Pointnet discriminator. Our approach is based on the pipeline of the deep SDF paper, but we improved it a bit to make it more robust. We start with taking 50 scans from 50 equidistant angles of the object, and for each scan we render a depth buffer. We then take this depth buffer and project it back into object space to obtain a surface point cloud. For each query point, we then calculate the shortest distance to any surface point to determine the distance, and to determine if the point is inside or outside, which will give us the sign, we project the point back into the view space of each depth buffer and then check its z-value. If the z-value is smaller than the depth value at that pixel, we consider the point to be outside of the shape for this scan. And if it's outside of the object for any of the 50 scans, we consider the point to be outside of the shape and therefore positive. We also open source our data preparation pipeline on GitHub. I want to quickly go over our network parameters. In each case, we use 128 latent dimensions. Our generator uses the same parameters as proposed in the DeepSDF paper. That means it consists of 8 fully connected layers, and each layer has 256 neurons. In the middle, there's a skip connection that re-injects the latent code into the network. For our voxel discriminator, we use a 3D CNN with 3D convolutions that have a kernel size of 4 and a stride of 2. That means each intermediate size is a power of 2, which means it's easy to do progressive growing. At the end, we have one fully connected layer with 128 neurons, and the final layer has one output neuron. The Pointnet discriminator uses 4 layers with weights shared across the point dimensions. The sizes are 64, 128, 256 and 512 neurons. After that, there is a global max pooling operations, and 3 fully connected layers follow. For the Pointnet-based scans, we use Pointnet sizes of 64 to the power of 3. That means they have the same amount of information as the voxel volumes we use for the voxel-based scans. This is in both cases at the final step of progressive growing. For a quantitative evaluation, we follow the testing protocol of A. Kleopdas et al. For each approach, we create a set of generated shapes and take a set of ground truth shapes that were not used during training. We use several difference measures between the sets of generated and real shapes. In each column, you can see the best performing method highlighted in bold. In summary, we presented 2 GAN approaches for 3D shapes. Both of them use the DeepSDF network as a generator. One uses a 3D CNN as a discriminator. The other one uses a Pointnet with an optional refinement step. During inference, the DeepSDF network can be queried at arbitrary resolutions. During inference, there is a possibility to generalize resolutions that are higher than the ones used during training. Our GAN could be improved by using other point processing discriminators. Furthermore, regularization schemes could be used to enforce valid sign distance functions. The source code for our project is available on GitHub. These are the sources for the presentation. For more sources, please refer to our paper. Thank you for watching.
Okay, so thanks for the nice presentation, and let's check whether we have questions from the audience. No questions yet. Okay, so I do have a question. So in a recent paper by Jaron Lippmann and his students, there was an approach to generating this implicit representation of shapes through neural networks, in which essentially they showed that if you use a penalty function which forces the function that you're looking for to vanish at the points of your input set, and you also impose unit norm gradient, you have this sort of regularization which produces really smooth and nice kind of shapes. So I was wondering whether you are aware of this work and whether this could be useful for the approach that you presented.
Yes, so we are aware of this work, and I think it's a very exciting and it's a very cool approach. We have considered to add this kind of additional constraint to our loss function, And I think we mentioned this in our outlook that this would be possible, and this is definitely something to look into, and I think this is very promising.
Okay, so let's see if we have other questions. No questions for the authors. Okay, so let's thank the speakers again, and we can move to the last paper in the session, which is titled Space-Time Blending for Heterogeneous Objects. And this is a paper authored by Alexander Tereshin, A.K. Anderson, Alexander Pasco, and Valery Adziev, and it will be presented by Alexander Tereshin.
Good day, dear colleagues. My name is Alexander Tereshin. I'm a PhD student at Bonn University, the National Center of Computer Animation. Today I'm going to present our work, Space-Time Blending for Heterogeneous Objects. To begin with, let me briefly describe the concept of the introduced heterogeneous space-time blending. Briefly, I will call it STB. First, let's give the definition of the STB and heterogeneous object. The STB is a geometric operation of bounded blending performed in a high-dimensional space, where the last coordinate will be time. In STB, both input and target objects are defined as functions, for example, distance-based. The most gradual geometry transformation happens in the time interval 0 to 1. In this picture, this area is marked as STB area. Heterogeneous object is a geometric shape that is considered in concert with its internal attributes defined for each point of the shape. For example, a simple scheme of such objects is the green cylinder shown in this slide, has a gradient color distribution in its interior. Let's consider that we have geometrical and color transformations that we have obtained somehow separately. We would like to combine these two transformations together to obtain a general approach in which geometry and color transformations will happen simultaneously and interconnectedly. Now we can formulate the major problem statement of this work that is subdivided into two parts. First, we would like to obtain an extended STB method that could handle geometrical and attribute transformations simultaneously and interconnectedly. The attribute transformation should happen in the high-dimensional STB space. It can be seen in the picture on the left that during heterogeneous STB we can see that geometry and color attributes are transformed together. Secondly, we would like to extend hybrid function representation with another hybridization of function representation with adaptively sampled distance fields. To apply a transduced method to the input objects, first we need to define them. The most common way of setting up objects is to use distance-based representations. One of them we will discuss here. Hybrid function representation is a distance-based representation that unifies advantages of function representation and signed distance fields, and compensating for their drawbacks. I will use a short name for it, HFREP. HFREP function is at least C1 continuous distance-based function that is positive in the interior of the object, equals 0 on the boundary of the object, and negative outside object. Its construction consists from 3 steps. On the first step, we define FREP object using function. FREP defines geometric object as closed subset of n-dimensional Euclidean space, using an equation that you can see at the first step. The actual field of FREP object heart can be seen above the step. On the second step, we use FREP function values for computing unsigned distance field. Unsigned distance field is the Euclidean distance from any point P to the surface of the object. The obtained field can be seen above the step. Finally, on the third step, we compute sign of the field to distinguish between exterior, boundary, and interior of the object. We use some step function taken from the FREP function values that equals -1 outside the object, approximately equals 0 on the boundary of the object, and equals +1 inside the object. The obtained HFREP field can be seen above the third step as a hard object rendered in 3D using sphere tracing. Now let me introduce another extension of the HFREP that is based on FREP and adaptively sampled distance fields. Adaptively sampled distance fields are distance fields that are obtained using hierarchical subdivision of the object, with further distance sampling according to the object's level of details. The construction of this hybridization will take 4 steps. On the first step, we need to define FREP object. Here we define treble clef using FREP functions and a certain number of set theoretical operations. On the second step, to construct ADF, we need to subdivide the FREP object using some hierarchical data structure, for example, quad tree. Then, on the third step, we need to compute distances at each corner of the obtained cells that we can see on the picture above second step. After it, we need to restore distance field in interior of each cell using some at least C1 continuous interpolation, for example, hierarchical B-splines. Note that in original ADF implementation by Friskin and others, field was restored at each cell using bilinear interpolation in 2D that leads to C0 and C1 discontinuities in the field. C0 discontinuities arises where the neighboring cells have different size, and C1 discontinuity arises because of the bilinear interpolation. The restored field can be seen above third step. Finally, we compute HFREP by multiplying obtained unsigned distance field by step function taken from the FREP function values. The resulting field can be seen above the fourth step. As we reviewed some possible approaches for defining heterogeneous objects, now we can consider the core method of the introduced technique, the space-time blending method. I remind the STB definition. It is a geometric operation of bounded blending performed in a high-dimensional space, where the last coordinate will be time. Here on the slide you can see the mathematical definition of the STB method. The blending function of B depends on 3 functions: the defining functions of 2 input objects, f1 and f2, and function f3 that defines the bounding solid. The aim of the bounding solid is to restrict the area where STB happens. To perform STP between 2 objects, we need to do the following steps. First, we need to raise their defining functions in a high-dimensional STB space by applying additional smoothing STB. Then, we need to conduct a set theoretical operation between 2 input objects. For example, it can be union or intersection. After it, we need to specify bounding solid defined by the function f3. We use a simple one defined as an intersection of 2 time planes. Now we can compute the displacement function disp_b. Here you can see 4 coefficients a0, a1, a2, and a3 that are manually defined. a0 controls the amount of material to be added to the resulting blending shape. A1 and A2 controls the symmetry of the blending shape, and A3 controls the influence of the bounding solid on the resulting blending shape. Finally, we obtain the blending of the geometry in time gap 0 to 1 that can be seen in the figure to the right. We can also see in the below part of the picture how geometry changes during STB. The mathematical definition of the displacement function is presented in yellow rectangle. And now we can see the space-time blending method applied to an HFREP hard object and an SDF cube that are defined without materials. This animation sequence was obtained without establishing any correspondences using Houdini. Now we are ready to discuss how we suggest to handle attribute transformation in heterogeneous space-time blending. To handle the attribute transformation, in our work, we suggest to use space-time transfinite interpolation that is defined in the same high-dimensional STB space. It depends on the values of the functions f1 and f2 that define input objects. In case of single partition objects, in other words, objects with specified distribution of one attribute, for example color, STTI is a simple weighted sum of 2 colors. In case the object consists from multiple colored parts, as we can see in the picture to the right, we need to compute the weighted sum of colors using formula at the bottom of the slide to obtain color transformation in the area between 2 objects. Now we can see the animation of the heterogeneous STB between colored HFREP object and SDF cube. We will discuss in more details on the next slide how to produce this animation in a step-by-step manner. The basic algorithm for applying heterogeneous spacetime blending to two input objects starts from defining these objects using one of the distance-based representations, for example sign distance field or hybrid function representation. In the next step, we need to assign attributes to the input objects using some attribute function that can be procedural noise, solid texturing, scalar field, or any other. After we define both geometrical and attribute parts of the objects, we need to raise them into high-dimensional STB space, where the last coordinate will be time. We can achieve it by applying additional space-time blending operation to these objects to obtain a smooth transition between them. Then we start computing space-time blending over all points or voxels, and for each point or voxel in which blending function is positive, we compute space-time transfinite interpolation for handling attribute transformation. At the end of this loop, we obtain full animation sequence of the in-between frames. Now let's see how the suggested approach works in an application called 4D cubism. Cubism was a revolutionary new approach to representing reality, invented at the beginning of the 20th century by artists Pablo Picasso and Georges Braque. In the left picture we can see a typical statue that is created in Cubism style with multiple features in the form of geometrical objects. In the previous work, made by my colleagues, an STB-based approach made in SideFX Houdini was introduced that makes it possible to convert such static artifacts into dynamic ones. You can see in the video one of the possible examples that can be produced using introduced technique. Let's discuss on the next slide how heterogeneous STB could be applied here. Basically, as you can see, the core of the basic algorithm for heterogeneous spacetime blending is pretty the same. All differences in the algorithm we have happened before computing the heterogeneous spacetime blending. First step is still the same. We need to specify two distance-based objects defined by functions f1 and f2. After it, we have two options. We can just follow the basic algorithm, or we can partition objects to specify colored features. To do so, we need first to remove those parts of the object where we would like to place generated features. Then, using octave data structure, we subdivide the object and specify features in the places where we have removed geometry. Finally, we do facetting, and the rest of the algorithm will follow the basic line. Now we are ready to discuss results we have obtained using introduced approach. In this example, we demonstrate the result of application of the heterogeneous spacetime blending to two homogeneously colored objects. We compare the results of applying STTI in RGB and HSV color spaces. As it can be seen in HSV, the color transition is reached in color gradations. It can be seen from the basic scheme of the HSV color space shown in the right picture that the interpolation in HSV color space happens radially, and more colors are participating in color transformation. On this slide we show a more complicated example with multiple colored features. Here we demonstrate the heterogeneous spacetime blending conducted between two colored SDF cubes with specified colored features, some of which are defined as SDF objects, some as HFREP objects. We also conduct current examples in RGB and HSV color spaces. In the rightest animation we demonstrate how color is transformed in interior of the object. In this work, we have presented an extended version of the spacetime blending method that could handle both geometry and attribute transformations simultaneously and interconnectedly. The attribute transformation is conducted using spacetime transfinite interpolation that also happens in the same higher-dimensional STB space. We have described the basic algorithm for defining heterogeneous STB that we further applied in 4D cubism application. They also briefly introduced the concept of the hybrid function representation that is based on function representation and adaptively sampled distance fields. As a future work, we are planning to extend 4D cubism application with more complicated attributes, including materials with different properties, for example such as transparency, luminosity, and some others. Thank you for your attention. Thank you for your attention.
Okay, so thanks for the nice presentation. And let's see whether we have some questions for the speaker. Okay, so no questions yet. I will start with a question that I have. It regards the types of attributes that you support. So you've shown something with scalar attributes. What if I have some vector data, for example, a cross field defined on the surface, or any other type of vector data defined on the object? Would it be possible to combine them?
As far as I know, basically about, for example, space-time transfinite interpolation, which we used, it mostly used for scalar type data like color or kind of simple textures. Can be also somehow applied, because I've also played around with this, but with 2D version of space-time, heterogeneous space-time blending with the objects with textures. So yes, it could handle only basically color or some sort of simple textures for now. For more complicated things, it should be somehow modified. And also for some complicated attributes which contain like subsurface scattering or similar things, the STTI method will not be able to handle it alone. There should be some more methods involved in this color transformation.
I see. Okay. So let's see if we have some new question arising from the audience. No questions. So thanks for the presentation, and thanks to all the authors who participated to this session. And the session is over. Thank you.
Thank you.
Thank you very much.